Okay, great. Well, thanks everybody for your interest and for coming to the webinar. Today, I'm going to present on mitigating seismic hazards with deep soil mixing. And thanks, Tim, for the intro and for exposing me as a skateboarder. But these days, I'm much better engineer than I am a skateboarder. So let's stick to the engineering today. All right. All right, so here's a little overview of the agenda. I'm going to talk in general about deep soil mixing, then cover three case histories here of projects where we used it to stabilize a slope, to mitigate surface fault rupture, and for foundation support. And then we should have some time for questions and answers. So first, overview of deep soil mixing. So this technique is just one of many, depending on how you count them, 40, 50 techniques that Keller provides as a geotechnical specialty contractor. I just want to emphasize that, you know, each site and each project is unique, and there is a technique that's right for each project. And that's one thing that Keller can do to help you out, is identify which ground improvement or deep foundation solutions are appropriate for your site and for your project. And don't hesitate to reach out to us if you need some help evaluating these things. We do this regularly as a service, and it's something that you can feel free to reach out to us. And there's some contact information at the end. So deep soil mixing is a technique where we use a large high torque drill rig, and we mix a binder that's typically water and cement in a batching plant. And then we pump that water cement grout down through the hollow stem of the Kelly bar and into a mixing tool that mechanically blends it with soil to create soilcrete. And the soilcrete has a compressive strength. Typically for design, the average strengths run from like 1,000 to 500 psi. And the typical depths of treatment run up to about 110 feet. That can vary even deeper in some cases. The columns can be combined to form panels or grids or clumps of columns. It's very flexible, the way that you can arrange them to pick up loads and resist seismic forces. And one thing to note is that the technique generates some spoils, because whatever volume of grout that you're pumping into the ground balances out and becomes essentially the same volume of spoils that come out of the hole as mixed soilcrete. So that needs to be, it can be either disposed of off-site, or if processed, it can make a really good compacted structural fill on-site. So here's a typical layout that you would see at a soil mixing operation from Keller. Number one, you have the batch plant up here in the upper right corner, where we have silos of dry cement powder. You see the delivery truck. We need room for a delivery truck to come in and charge those silos regularly throughout the day. In the middle, there's the tank, where we are mixing the water and cement to make the grout, and then it's pumped over to the rig down the hole. And you see the deep soil mixing rig doing the mixing itself. You also see a pre-drill rig that we sometimes use to either pre-loosen holes or to create a cavity to allow some of the spoils to fill in to the cavity, as opposed to you know, having to, if you're hauling them off site, that's one way of reducing the amount of spoils, is to create a cavity. You see a loader. We typically would have a loader and or a excavator sort of moving spoils around. And then you see a coring rig up here, where we're doing our quality assurance coring of the columns, and I'll talk more about that later. Here's a couple other photographs. On the left side, you have the batch plant. On the right side, the soil mixing rig with the wet soilcrete previously mixed panels, or columns rather, along a panel. And you can see that this, you know, the wet soilcrete is sort of like a peanut butter shake kind of consistency. And within a few hours, typically it's going to set up. But you need to be careful around the wet soilcrete holes, and safety is an issue. We typically are barricading and blocking areas off so that people don't walk around or equipment doesn't come close to the wet columns. So here are some examples of different configurations that we can use for various applications. On the left, you have panels, shear panels that we can arrange to resist slope instability. In the middle, you have isolated columns, which can be used primarily for settlement mitigation. And on the right, you have a lattice grid of intersecting panels that can be used for liquefaction mitigation primarily, or for seismic static settlement mitigation as well. So when we talk about deep soil mixing mitigation for seismic hazards, we have three sort of effects that are occurring when we do deep soil mixing. One is solidification. So whatever material that we are actually mixing is going to be turned into a solid that's something like a soft rock. And then we have shear reinforcement. So you're not mixing, typically we're not mixing 100% of the soils. So any soils that are left in between, like in the lattice grid of panels, is sort of shielded by the shear reinforcement of the DSM grid. And I'll talk about that a little bit more in a minute. And then for foundation load support, we're able to, put these underneath the foundation so that we can just take up the loads in the DSM, and it's acting kind of like a deep foundation in a way. So for the shear reinforcement, there's been some research that has been done on this topic. And basically, a series of numerical analyses and centrifuge experiments were done where we looked at, okay, how much of the shear stress is going to be taken by the DSM versus the soil that's left in between the DSM cells. And these relationships were developed where we could estimate what is the shear stress reduction, or the cyclic shear stress reduction, of the soil in between the panels. And this chart shows the results of that. G sub R is the ratio of the shear stiffness of the soilcrete to the soil. So that typically is ranging around 20, 30, something like that. And AR is the area replacement ratio. So that's just the area and plan of soilcrete divided by the total area. And with deep soil mixing for liquefaction mitigation, we're usually ranging in this sort of 25% to 50% range for AR. And like I said, around 20 or 30 for the GR. So with that kind of range, you can get these R sub RD, that's the reduction of the cyclic stress ratio, or if you will, you can think of it as a reduction in the seismic demand or peak ground acceleration that you're using for your liquefaction analysis. Those reductions are on the order of 90 to 80%, which is very significant. So if you're taking a PGA of 50% of gravity and reducing it by 90%, you're going to end up with a very small PGA that probably won't trigger liquefaction anymore. And for bearing capacity, we designed the soil mix grids to support foundation loads without contribution of the soil in between. So even if there is some minor liquefaction that's left over that the shear reinforcement doesn't take care of, we're still going to design these DSM grids to support the foundations without any contribution from the soil whatsoever. We just need to check the DSM crushing strength to make sure that we have adequate bearing pressures for the foundations. Quality control and assurance is a big part of a successful soil mixing job. It starts for us at Keller with a data acquisition system, which records data from our rigs, which are very heavily instrumented. We're recording things like the time, the depth of the tool, the rotation speed of the tool, the hydraulic pressures for for crowd and for torque, the grout flow rate, the grout specific gravity, and other parameters that really allow us to track what's happening in the ground very well. And we process that data to give us some critical parameters that are shown on this data acquisition report. And on the left side, you have the blue line, which is the binder content. So this is the dry weight of cement per cubic yard or per cubic meter that's left in place in the ground. And we're typically targeting a value that, based on our experience and maybe a bench scale test, is going to provide us the unconfined compressive strength that we're that is, you know, for the design. And you can see that the blue line is targeting on these dashed black line, which is our target value. And all of our rigs and our systems basically have a automated pumping system where we're monitoring by monitoring the specific gravity, we're measuring the amount of the cement that's going into the ground, and we are automatically varying the pumping rate to adjust to differences in the penetration rate so that we get the right amount of cement in the ground. And that is done automatically without the operator of the rig having to really even do anything. The other line in this plot, the red line, is the blade rotation number, and that's the number of rotations of each blade of the soil mixing tool over a 1 meter vertical interval. So this is an indication of how much mixing energy is getting into the soil, and it's an important parameter to maintain at certain levels that depend on the soil type. Clays are typically more difficult to mix and require a higher BRN than sands, but anyway, we monitor that to make sure that we're getting enough mixing energy into the ground. The drilling index is a sort of indicator of the difficulty of the penetration rate of the tool into the ground, and that can be helpful if you're targeting like a certain bearing layer. It's not the case for this one, but you'll see if you hit a hard layer that this line will go up like this so that you can confirm that you're in a bearing layer. So this is all happening while the mixing is being done, and the operator is seeing a live readout of this stuff in the cab. And within a few minutes of the soil mixing column being completed, our system will shoot this off to the internet, where it becomes available to our design engineers and consulting partners to take a look at it in almost real time as the work is being completed. Over here, you see a core. So we do core the DSM, and we look for the continuity and the homogeneity of the mixing, and have requirements typically to satisfy that in a specification. We take wet grab samples. Here's a field engineer taking a wet grab sample out of a trapdoor bucket that we push down into the soilcrete column, grab the sample, and then we cast it into cylinders, typically 3 by 6 inch cylinders, and then break them at different curing times. And you see there is a strength gain with time with soilcrete, just like there is with concrete. And we typically target the 28-day strength as our specification compliance strength, and but we monitor the strengths to make sure we're on track to get to that 28-day strength during construction. We also will break specimens up from the cores itself, and typically the data kind of is consistent between more or less consistent between the grab samples and the cores. Okay, so let's look at a few applications of soil mixing. Here is a project in the San Francisco Bay Area. It's a redevelopment project of a power plant along the bay shore here. It's going to be redeveloped into multi-purpose, multi-use kind of application with a beautiful waterfront fronting on the bay, and you can see the San Francisco Oakland Bay Bridge in the background. It's a beautiful site. But the site is like most sites around the San Francisco Bay margin, is underlain by young bay mud, which is a normally consolidated to slightly over consolidated clay that is subject to cyclic softening under strong earthquake shaking that we can have in the San Francisco Bay Area. And then it's overlain by old fills that had some liquefaction, liquefiable sands within them. And the geotechnical consultant determined that the slope would be prone to 2 to 4 feet of seismic slope deformation as a result of the maximum considered earthquake at the site. This slide shows some of the geotechnical conditions based on the CPT data. You see here from 30 to 50-ish feet is a Young Bay mud layer. It's got an undrained shear strength around 1,000 PSF at this depth. You have this variable fill in different layers. Some of it's liquefiable. Underlying the Young Bay mud are more competent, very firm to, or very stiff to hard clay layers and sands. Basically competent material. So to stabilize a slope like that, like this, we can use the shear panels like I showed to you earlier. There are some good references for this in the literature. The FHWA 2013 design manual for DSM is a pretty good one, although it's focused mostly on static criteria and static projects. It requires some adaptation for seismic purposes. Another good reference is Boulanger and Shao 21 from the soil mixing conference, the DFI soil mixing conference in Poland. I have all these references in the last slide of the presentation in case you want to get copies of them. So we do design checks for global stability, overturning and sliding, the shearing on the vertical planes if you have where you have the overlap of the columns, for bearing capacity, and for extrusion or flow of soil in between the panels. And at this site, this is basically what our layout looked like. From the plan view you see here, we had, what was it, 11 columns overlapping. I think these were 6-foot columns overlapping in a secant way, and that's what it looked like for plan. And this extended, they were typically spaced around 20 feet, and this extended quite a ways in either direction along the front of the water. And then if you look at it in cross section, this is the lower diagram. The depths varied in order for us to get embedment into the component layer, and they were varying up to 75, 80 feet. Some are probably more shallow, like 50, 60 feet. So in this design, we went about it using performance-based methods where we're looking at what are the expected deformations and what is the engineering performance. And here are some examples from different earthquakes of deformations that have occurred as a result of liquefaction lateral spreading on the bottom two, and as a result of liquefaction flow failure on the upper right at the lower San Fernando Dam failure from the 1971 San Fernando earthquake. So ideally, we would like to use advanced numerical methods to predict displacements for performance-based design when possible. This project was able. We had the time and the requirement to do this kind of advanced analysis, and we went about it using the computer program FLAC, which is a finite difference method program. Here you see the model on the top with the soil layering and with the finite difference mesh. This is without the DSM buttress, and then the lower one you see here, we put in the DSM buttress. That is a composite material based on this sort of smeared composite stiffness and strength of the DSM and the native materials. We used the PM4 silt model for the Bay mud, and we calibrated that very rigorously to published data and some of our site-specific shear strength and shear wave velocity data. The calibration process starts with matching the modulus degradation and damping curves as best as possible, and then you look at the cyclic softening effect and the cyclic strength of these materials. And we also We also used PM4 sand for the liquefiable fill materials. I don't show that calibration here, but that was also the other critical model used in this analysis. So here we have the unreinforced slope in the top, and you see that we're getting about 2.5 feet of slope displacement at the crest of the slope. This agreed pretty well with the consultant's estimate of displacement. And then here with the DSM buttress, you can see that behind the DSM buttress, we're controlling the displacements very well. They're basically less than 3 inches. And we still have a lot of movement of the slope in front of the DSM, but even with this material displacing a foot or two and pulling away from the DSM still remains stable against overturning and sliding. And I should say that typically to achieve this, you need a DSM buttress that has a width to height ratio on the order of like 80%, something similar like you would do for any kind of gravity wall or MSE wall. So we compared the nonlinear deformation analysis from FLAC with the more conventional limit equilibrium analysis. It's always good to do checks with more simple conventional methods when you're running a more advanced model. And in this case, we got similar displacements. The FLAC displacements, depending on time history and polarity that we use, were about 0.75 to 2.5 feet. And when we looked at the displacements with a Newmark type analysis with the Brand-Macedo method, we were getting median displacements of around 2 to 3 feet. But if you account for the standard deviation or the variability of those displacements, you probably get a much wider range than what we estimated with FLAC. And that's probably one of the big benefits of running FLAC, is that you're going to narrow the band of possible displacements. Typically, if you have a well calibrated and controlled set of ground motions, compared to these more generalized simple methods, which will give you a wider range if you account for the uncertainties involved in it. The other thing that you get out of a FLAC analysis is a much better understanding of the patterns of deformation that are possible at the site, whereas with the simple methods, you're just looking at this split, as one single slip surface and the displacements along the slip surface that are possible. So with the DSM, this is the result that we get that I showed before on the top, and then the simplified method. Again, we got similar results, but again, the deformation patterns are much better and easier to understand from the FLAC analysis than they are with the simple method. So here's a few photographs from the construction. You can see our rigs at work here doing the soil mixing. It looks like we're working like right next to the water, but there's actually, I think the grade was more like 14 feet or so above the bay, so we're not mixing soilcrete right into the water or anything like that. There's a good separation here. So on the right side picture, you see the DAC readout that the rig operator is seeing when he's doing his work, and that allows us to control the operation very, very well. Okay, the next project is a pretty unique one. It's on surface fault rupture mitigation. And at this site, this was at a water treatment plant, and you had a pipe coming in, a large diameter pipe, 120 inches. The project was that they need to tap into this and redirect some of this water to other places in the plant. So the project was to build a junction box, and from the junction box would run these pipes over to these wet wells, and the wet wells would pump the water elsewhere in the plant. So these wet wells are extending down below the ground surface. And then there was an above ground structure for the pump station. And if you look at a cross section cutting through here, it'll cut through the wet wells and the pump station. This is what it looks like. At the site, you had medium stiff silt and clay layers in the surface with loose to medium dense silty sand that was liquefiable. This is about, I don't know, 15 feet deep or so. And then you had medium dense to dense sands mostly below that were fairly competent, bits of liquefaction here and there. There was a liquefaction lateral spreading hazard at the site, but the biggest problem was that there were active earthquake faults going through the site. And this is a very congested site and not possible to site this pump station anywhere else within the water treatment plant. So we had to mitigate the seismic hazard of the faults going through the pump station. Now, if you have a structure that's just at grade with faults intersecting its location, the best strategy is just to build a big mat. There's been some projects where they'll put a reduced friction interface at the bottom of the mats that allows the ground to displace. This is for right left. This is for strike slip faulting. That allow then you can just allow the ground to move underneath the mat, and the mat can just kind of surf it out with all the trouble happening underneath it. But when you have something that's sticking down into the ground across a fault, it's a condition like this tree where the roots of one side of the tree are on one side of the fault, and the roots of the other side of the tree are on the other side of the fault. When the fault displaces, they're going to grab into each side of the ground and rip the thing apart. And that's kind of what we would expect to occur at the site with these wet wells. So what we wanted to do with a mitigation strategy is to make it monolithic, like this telephone pole intersected by a fault, where there's a lot of evidence from field observations where big, strong monolithic structures that are intersected by faults can stay and act as a rigid body and let the faulting move around it. So our strategy to mitigate that was to build a big block of deep soil mixing where the faulting would come up, hit the soil mixing, and the whole thing would the faulting would deflect around it, and the whole thing would act more or less as a rigid body. So as far as we could tell, this was the first project that took this approach, and so we wanted to be pretty rigorous in our evaluations to make sure that it would work. So we used a 3-dimensional FLAC model, and it was a pretty large domain. It included a lot of details, including the faults. So we used interface elements for the faults, and it included the structure of the pump station, which I'll show you in a second. Let's see. And the wet wells and so forth. So we explicitly modeled all the elements that were important to the behavior. That we were trying to confirm that the DSM acts as a block without rupturing. And we calculated the displacements of the structure and then provided those to the structural engineer who performed their own check on the structural performance. And we also provided displacements to the pipeline designer who designed the pipes with flexible connections to accommodate any displacement that occurred. And there's a lot of important elements to this kind of modeling for fault rupture, but one of the key things is to use a material model that includes the ability to do strain softening. Because what a surface fault rupture does is that it will concentrate the slip at a plane after the material has been sheared enough to basically reach a residual strength. That's why we see concentrated slip and faulting, because you've mobilized a residual strength. So you have to have a model that is able to do that, and there's a fair amount of research on this topic. So this is what the model looked like. You see this is the overall model cut in half, and then here we have a close-up on the right side. You have the deep soil mixing block, which is in magenta. You have the wet wells, which we modeled with plate elements in FLAC. We included the mat of the building foundation and the walls of the building. Originally, we didn't include these building walls, the building itself. And when we provided the first set of analysis results for the wet wells to the structural engineer, they're like, this is impossible. There's no way the structure is going to move this way. And we said, well, this superstructure is going to provide a good amount of stiffness that we're not including in the model at this point. So we took the time to go ahead and add that in and rerun the analysis with it. And then we were able to generate some more realistic and compatible displacements with the structural engineer's model. So the faults come up here in red, and we basically put slip on one side of the fault and hold the other side steady. And so here are the stages of the modeling. You start with the site, put the DSM in, build the structure and the faults. And then here you can see these are actual model results of the displacement of the faulting. And there was a full seismic hazard analysis with the surface fault rupture that I don't have time to go into, but these faults, we weren't sure if the slip could happen on distributed across them or on just one of them. So the worst case scenario from an engineering standpoint is all the slip on one. So what you see here is all the fault slip happening on one of the strands. And the default displacement that we used was 1.5 feet of horizontal and 4.5 inches of vertical. These are actually secondary faults off of a primary fault that could displace a lot more than that. So the first thing to do is to run the model without any structures in the way. And you want the model to show that it can, that you're going to get concentrated slip at the fault interface. So this is what this result is without any of the structure there. And so we're basically, in FLAC, what you're doing is you're putting a velocity on the sides of the model and on the bottom of the model, and you are holding that velocity until you reach that design displacement. Then when you put the structure in the way of it, you'll see that this what was the concentrated slip in the free field now gets very evenly distributed. And basically this whole soilcrete block did act like a rigid body, more or less. It did have some internal shear straining in it that was reflected in the results, but that was the degree of that was acceptable for the structure. And you see that the slip is coming up from the bottom, it hits the DSM buttress, and it just gets distributed around, and the whole thing kind of rotates like a rigid body. So this is what the DSM elements look like. So we need a full 100% soilcrete block. So all of the columns had to overlap with each other. And the design average strength was 500 PSI. And this is what the layout looks like. You see the color, different color, green and blue is where the wet well is. These are some photographs from the construction. And here's what it looked like after the soil was mixed. Remember, these upper materials were loose sands and softer silts and clays, and now they are sandstone. And they are excavating in this. This is a 30-ish foot deep excavation that doesn't even need to be shored because it's basically sandstone now. All right, last one to share with you here is a sort of more conventional project. The surface fault one is kind of unusual, but this is a more conventional project. Here we have some fuels, aviation fuel storage tanks, new ones. There's a couple of existing ones. This is at the San Diego airport. So these are the existing ones, and the project was to build 3 new ones. If we look at a cross section through the site at the soil conditions, we have some fill in the upper 10, 15 feet. It was mostly sandy. It was liquefiable. And then we have bay deposits which were interbedded soft clays and medium dense to loose sands. The sands were typically liquefiable. The bay deposit, the clay bay deposits were highly compressible. And so the problems at the site were with liquefaction, seismic bearing capacity, and static settlement and bearing capacity. So the solution was to use a mat foundation for the tanks and to build them on top of a deep soil mixing ground improvement zone. So a little bit about the liquefaction mitigation. Here's some CPT data, and you see the red zones are zones where we have factors of safety of less than 1 for liquefaction, and a little bit right here. So this is this solid red line rather is the cyclic stress ratio without any ground improvement. And then when we account for this shear reinforcement, we get about 2 inches of seismic settlement with that. When we account for the shear reinforcement, we are going to reduce the cyclic stress ratio by about 90%. And that's what you see here, the cyclic stress ratio reduction. And that's enough to make the factors of safety larger than 1. So they're all plotting like off the chart over here, larger than 2, and basically eliminates the liquefaction from the site. So this is how the liquefaction mitigation works. For the static settlement evaluations, we break it up into 2 components. This is typical for pretty much any ground improvement technique where you're looking at the compression of the DSM zone, which is relatively small. Typically that's going to be on the order of a 1/2 of an inch or so, because the DSM is very stiff, and then you're looking at the whatever's left below that, the settlement of the soil below that. You're also checking the crushing strength of the DSM from the foundation loads applied at the surface, and you're checking at the geotechnical bearing capacity for the DSM bearing on the soil below it. We run it for tanks. We typically run a check of edge stability for static and seismic conditions in case the soil outside here liquefies and becomes very soft. We don't want the edge to become unstable and shear off. So we'll run a check here using a slope stability method. And this is what the layout looks like. So we have a grid on the under the tanks, which is basically achieves this area ratio that's required for the liquefaction mitigation and for the bearing capacity, static bearing capacity and settlement. You'll see around the edge here, there's a continuous panel that was placed underneath the containment wall. So they wanted the containment wall to also perform adequately in a seismic event. And then we also have some isolated columns here for support of for the piping and that's running to and from the tanks. And so for these columns out here, these isolated ones, we're not mitigating liquefaction. So the soil would be expected to liquefy around it, and you have a down drag that can occur after the soil, the pore water pressures dissipate and the soil settles. So we design for that down drag and make sure that it's going to work okay, even with the seismic down drag in case like that. Here we are in construction. I'll show you how quickly our crews and equipment work. Here you go. So this is the rig. So this is a time-lapse video basically of the rig constructing some columns, and it's a little bit slower than that in the field, but the work was completed successfully, and those tanks are now standing. Here's a picture of the tanks. You'll see them if you fly into San Diego. Just look over to the right when you're landing, and that's that. Okay, so here are some references that for some of the papers that I mentioned, and we have some time for Q&A here at the end. So please type in your questions into the Q&A. You'll see a Q&A icon in the Teams window, and you can type in your questions here. So let's see. Okay, so here we go. Hopefully let me try to start with the first questions first here. Let's see.
Yeah, and if you go down through some of these, Jim, you can see, click on the comments. I've answered a lot of them, but there's a few here that are kind of perhaps maybe beyond my capability of BSing.
Okay. All right.
I haven't answered that first one about installing a transfer platform for the tanks.
Yeah, okay. Yeah, you're getting most of these questions here, so. What's the behavior of the DSM mix under dynamic loading? Any degradation to be expected by seismic action? That's a good question. There is a little bit of data out there in the literature on the modulus degradation behavior of the DSM. We typically, when we model it for numerical purposes, we would use more like a secant stiffness and a strength, and in that way we would capture any non-linearity of the DSM. We also recently we've been using a strain softening model for the DSM because the residual strength, if it does fail, is lower than the peak strength. Yeah, is there a decent rule of thumb for the panel width to depth ratio for lateral spread? Usually it's about 0.8, so the width needs to be about 0.8 of the height. And that's mostly for overturning resistance. If you can put in a really slender and strong element into a slope stability analysis and calculate a factor of safety that's high, but you have to account for the possibility of that thing to overturn and look at that mode of failure, which your slope stability analysis isn't going to give to you. There's more steps than that.
I stand corrected. I removed my answer, so good, thanks.
Let's see, cost.
How about dynamic loading? What is the behavior of DSM mix under dynamic loading? I think you did answer that, didn't you?
Yeah, I got that one. There's one about, did you install a transfer platform for the tanks? No. So the preferred method for soil mixing is to run a mat analysis, a Winkler analysis of a mat, where we provide a subgrade modulus for the DSM and a subgrade modulus of the soil, which is very low, and let the structural engineer run that to determine the mat shear moment displacements. That's the preferred method. And typically by doing that, we find that we don't need a load transfer platform like you would if you were doing rigid inclusions.
And I see people are posting questions on our team site. If you would just please move those to the Q&A button on the top here so we can consolidate all the questions into one area.
Yeah, okay. It's the way that they come in, it's kind of backwards, so
yeah,
just trying to make sure that I get all of them. What's a good reference for checking extrusion flow slide of the soil between the panels? The only one that I know of you have two options. One, there's a method available in the FHWA manual, or number two, you could run a three-dimensional analysis. That would be the most rigorous way to do it. And we've done that in some occasions in the past. The FHWA manual is a little tricky to apply for seismic conditions, but it can get you an answer that is, can work for you. What frequency of testing would you say is typical for wet grabs sampling? How about coring? Good question, Paul. We typically do wet grab sampling once a day for each crew or each rig, basically. And for coring, the frequency can vary anywhere from 1% to, I don't know, 3%, or some people that are very conservative might be 5%, but you got to be careful and think about how many cores that actually is going to be and what kind of cost that's going to add, and balance that against the quality concerns in the project. What's the Young's modulus of DSM? Have these DSM columns been exposed to actual earthquakes? And if so, how did they perform? The Young's modulus is typically estimated as a function of the unconfined compressive strength. The FHWA manual recommends 300 times the unconfined compressive strength, so that's something that's used a lot in practice. Yes, there have been many cases where DSM columns have been subjected to earthquakes in Japan and Alaska. Not sure if there was anything in Christchurch, but yes, there have been many case histories of DSM columns performing very well in earthquakes. Hey, John Lee, how's it going? What is the criteria of recycling DSM spoils as the compacted material? Is the crushing process of the cemented spoil required? So usually what happens is that we will, as the soilcrete spoils come out, they're being moved around and stockpiled, and in that moving around and stockpiling process, you're kind of breaking it down as it's setting, and that is enough to make it more soil-like and not, like giant clasts of hard material. So that's typically enough to make it useful as a structural fill. How can you control the heave that might happen due to DSM construction? We don't see heave happening in DSM construction. It's just there's not a mechanism for that, at least that I've seen. Are there any specifications for laterally loaded DCM for slope protection? I assume you mean DSM for slope protection. So you have to be careful with columns for laterally loaded slopes because they go into bending and they don't have reinforcement and they don't have a lot of bending capacity. There's a case history from Japan where isolated columns failed due to too much lateral loading. That's typically why we're using panels instead of individual columns if you have a lateral stability issue. As long as only cement is used in the DSM, how does it behave under water? There's no problem with groundwater. Water is what hydrates the cement, so it works just fine under groundwater. In design, how to incorporate variable strengths of the DSM area that extend through various soil types. We are typically, when we evaluate the DSM strengths, we're typically accounting for the various soil types and basically we're targeting the lowest strength that we're going to get, or accounting for the lowest strength that we're going to get in the design based on the soil types. So we typically don't zone the DSM strengths in a design analysis. We look at it in more of a statistical method, statistical approach. Do you use the method of FHWA manual for checking extrusion between panels? Yeah, we talked about that a little bit. Yes, we do, but it is a little bit squirrely. But it's something that we do look at, yeah. Let's see. Okay. Is there a general answer to what is the strength reduction factor UCS between lab prepared DSM samples and field application? That's a good question. And ironically, we find that we often achieve even better strengths in the field than we do in the lab. And the reasons for that can be many, but in general, we are at Keller, since we're mixing soilcrete every day all over the place and have a lot of experience in doing so, we feel more comfortable with basing our strengths on our experience and then proving them in the field. We do run bench scale tests now and then, but there have been cases where bench scale testing has come up 50% lower than our field strengths, and we maybe a little, maybe not quite that low, but usually, we really rely on our experience and what we've achieved in the past at mixing at different sites. What's the largest DSM panel depth and width from past projects? Boy, there have been a lot of panels that are very wide, great widths that have been used on dam projects, for example, to get enough shear resistance. Depths, I think for, I don't know, we typically max out at 105, 110 feet, something like that. We did a project in Portland recently that had some panels that were that deep, and they were probably 80 feet wide, something like that. Do isolated columns still have their place in liquefaction mitigation, or are these all but ruled out and only used for static? I think isolated columns have some place in liquefaction mitigation, but they just need to be used with caution because of things like kinematic loading and bending that could occur. But I think there are some cases where it's okay to do that. One question on difference between DSM and jet grouting. Both jet grouting and deep soil mixing result in a column of soilcrete. One of the main differences is the column diameter varies with jet grouting. Is this your answer, Tim? Is that an answer?
Yeah, sorry. Yeah, that had been posted on the one site,
Gotcha.
and I put that up there.
Gotcha. Let's see. We're still good on time. I'm going to keep answering questions as long as there are some, and there are people here to listen to the answers. So I'd rather do that than write back. So I'd rather take care of them here. So let's see. Are there any sites you've seen where it makes sense to install aggregate piers below structures, but install DSM as a lateral spreading wall because that hazard is not fully mitigated by aggregate piers? Yeah, very much so. I mean, the strength difference between aggregate piers or stone columns and DSM is significant, and the DSM is much stronger, much stiffer, much easier to stop lateral spreading than aggregate piers or stone columns. So there are plenty of conditions where the stone columns are just not enough, and you need to go to DSM. Now and then we can get it to the stone columns or aggregate piers to work. How is the column construction monitored, controlled during construction for deviation from vertical axis? Yeah, our rigs have a what do you call it, Tim? Plumbness measurement of the Kelly bar.
Let's face it, you always set these things up to do vertically. They act kind of as you go deeper as a big plumb bob. And it's basically set up as you're starting the column.
Yeah. Let's see, how would you account for the cracks, say tensile cracks, any mitigation of or pressure from nearby liquefiable soils? Okay, the second question is easy to answer. So the soilcrete is essentially, for all intents and purposes, during an earthquake, it's totally impermeable. So you don't, unlike stone columns where there's some concern about mitigation of pore water pressures into the ground improvement zone, that's just not going to happen with soilcrete. And because of that, you only need to treat up to the edge of your structure and not have a buffer zone outside of it like we do with stone columns. So that's one thing that I've seen from time to time consultants didn't understand, and they say, okay, you got to go, half the treatment depth outside the building with with soilcrete. You don't have to do that because there's no concern about the pore water pressure mitigation. How would you account for the cracks, say tensile cracks? Tensile cracking, I mean, it really depends on the application, but you should, if you're doing numerical modeling, we have seen some tensile cracking in cases where we're putting lateral loads on soilcrete. And in cases like that, we would look to see, okay, well, what's the consequence of that in terms of displacements? We don't necessarily design for it to never go into cracking. We design for acceptable performance. Is there a reference that shows comparison of measured dynamic responses between soils within and outside the DSM lattice grid? Measured dynamic responses inside and outside the, that's a good question. I couldn't tell you off the top of my head. I'm sure there's somebody that has done some broader numerical modeling of a DSM system, but I'm not, the work that the cyclic stress ratio reduction is based on is from unit cells that don't look at inside and outside the grid, but I'm sure somebody has done some work like that. I'd like to see it if you can find it. For the slope stabilization case history, what were the seismic design criteria and what was the return period of the design earthquake, given that the waterfront upgrade does not appear to be a building? There were buildings, yeah, behind that were being protected by the deep soil mixing buttress. And so we were using the maximum considered earthquake, which is the 2475 return period. The San Andreas fault at that site is only 3 or so miles away, so the seismic demand was really quite high. I think the PGA was 0.8 or so, 0.9. So really high seismic demand. The displacement criteria was for 6 inches or less of displacement. Is there an inclinometer in the DAC? I think we kind of talked about that. There's one, yeah, an inclinometer basically on the mast of the drill rig. So it's measuring what what the Kelly bar is starting at when you're going into the hole, but if there's deviation because of a deflection off of a obstruction or something like that, then we're not necessarily going to be able to measure that unless the mast tilts with it a little bit. Is the consistency of the completed DSM column in a soft clay? How's the consistency of the DSM column in a soft clay like Bay Mud? It's really good. We're really good at soil mixing. I'm not just saying that. We are able to get good mixing, and even in San Francisco Bay Mud or any other Bay Mud, and we get 100% core recovery all the time with very few inclusions, and strengths in the 100 to 200 plus psi range. Any monitoring data available on the effect of installation of DSM on nearby infrastructure? It's a pretty good technique if you need to work nearby infrastructure, because there's not a lot of abrasions. The one thing that we do have to work to watch out for is there have been cases where we're installing DSM adjacent to shoring systems. So if you're within an excavation and you're in the zone where the shoring system is counting on passive pressure, and you're going to go mix right in front of a soldier beam, you're going to change that 350 or 400 PCF passive pressure into a fully liquefied material with a fluid weight of 120 or whatever pounds per cubic foot. So you're reducing the passive resistance temporarily until the soilcrete is cured. So there are ways to work around that. Typically what we've done is put a whaler along the toe of the wall to tie it in together, so that and then do a sequence of mixing where you're mixing one soldier beam and then letting it cure before you go on to the next one next to it, so that the soldier beams on either side can take the load temporarily through the whaler while you're mixing one of the columns. Do you do FEA modeling for most DSM project, or is that mostly for these unique large projects? We certainly don't do it for every project, but we're doing it with more and more frequencies, especially even for static settlement modeling. It's just it allows you to not have to make a bunch of assumptions and simplifications in your analysis. And at the end of the day, it's what I found is, for us at least, that it's just more efficient, and in the end you save more time if you just bite the bullet and do the modeling in the first place, rather than try to use a simplified method and save time, because ultimately you might come up with some questions and uncertainties from the simplified method, and you're like, well, the only way to really get our arms around that is to model it more explicitly, and then we end up doing the modeling anyway. Is there a correlation between mixing energy to strength in certain type of soil? Not directly, but you need the right amount of mixing energy to, or mixing work to get good homogeneous soilcrete. Any thoughts on CPT testing versus coring to evaluate installed DSM columns? That has been done. It's a cheaper, faster way of getting some data, but it's a little, it's more qualitative, I would say, because if you wait for 2 weeks, you're probably not going to push that CPT into the DSM because it's going to be too hard. And so you have to do it at some intermediate curing time. And so then the magnitude of the penetration resistance is really, depends on how much curing has happened. You might see in it like zones of, if there's any unmixed zones and stuff like that, you might see it, but then it just becomes, it's very qualitative. And at the end of the day, I think it's just better to have coring data than CPT. If you want to supplement the cores with CPTs, I would say that's great, but I would do that with pairs. I would make sure at least you have some calibration of the CPT against the coring data, so that you can make more sense out of those CPTs. Have you investigated the durability of an exposed soilcrete face? Not like in a long-term way, but as far as we know, there's no long-term degradation of the soilcrete. So can DSM columns be installed only into targeted confined layers, or do these need to be continuous from the ground level? Yeah, they need to be continuous from the ground down, because you're mixing from the ground down. There's no way to avoid any layers. But if you have a situation like that, then you can use jet grouting, because jet grouting, we can drill down to the target zone and then jet and pull up from there and stop at the top of whatever zone. But jet grouting makes soilcrete too, but it's more expensive. Okay, wow. I think I'm exhausting the questions here, so should I look in the chat, Tim?
Sorry. I think the one thing people were asking is how deep has it been done, and I think you answered that, but perhaps we should revisit that. I think generally we're going to 80, 90 feet, sort of on a regular basis. Below that, you're probably reaching the limits at 130, 150 feet.
Yeah, and I think most of our equipment maxes out around 105 feet, but there could be exceptions in our fleet, and there may be other contractors with different capabilities. So if you had a project where you really needed to go deep, I would say call us up and let us look at the specifics and what we could do, and go from there.
Yep. Size overlap. Another last question.
We got a couple more. Size of overlap in the secant soil mixed columns. Yeah, so that depends on the application, where you need, we're using them for lateral loading, and you need to make sure that you don't have the racking failure with the shear on vertical planes. You want more overlap. Be more careful about the overlap. This is an area that, in my view, needs more research. There's a method for looking at it in the FHWA manual, but it's really geared towards the static loading condition, and it's difficult to apply for the seismic loading condition. So this is an area where more research is needed, and we have some plans to take a look at it, at least from a modeling standpoint. Can you talk about selecting between dry and wet soil mixing? In North America, typically we're almost all wet soil mixing. So wet soil mixing is where you're mixing cement, dry cement powder and water to make a grout and then pumping that down into the tool. Dry soil mixing is when you're pumping using air, you're pumping just the dry cement powder into the ground. So it's for cases where the soil it has enough water in it already that you don't need to introduce more water. You don't want to introduce more water. I think it's fairly common for the Norwegian clays, Tim.
Yeah, and it's interesting. We did actually use the dry method in Oakland in bay muds, and we found that the bay mud was still not wet enough, so we had to introduce some water to that. So even a San Francisco bay mud is too dry for dry mixing.
Yeah, for dry mixing, you consistently need a water content of 50% or more. So it's tough to find sites like that. You typically like need to go through some fill, or you want to go through the bay mud and into some other material, and you're just not going to maintain that high moisture content throughout the entire profile. So that's why it's pretty rare to use in North America, at least.
There's another question about clarify if this is good for all types of soils, including peats, and I would say yes, except, then we do have to figure out what kind of peat you have and the extent of it and all that stuff. Peats can be questionable, correct?
Yeah, we've mixed in peats before with success. So, but it would depend on the amount of peat and the nature of it and what kind of strengths that you have to be careful about the strengths that you would achieve. It's preferable to remove it. If it's shallow, it'd be a nice material to pre-excavate out, but that's one of the great strengths about DSM is that it's really applicable to material types, a wide range of material types from sand, silts, and clays.
Well, I think we're just at the end of the presentation. We'll continue this in the bar later for those of you who are going to stay with us, but thank you all for your time and attention on this, and we wish you great success. Please stay in touch with us. If you want any further presentations out west, feel free to contact me or just go on our website at keller.com, and you can find all of our contact information across the country if you'd like a presentation or more information in your area. But thank you all for attending.
Yeah, thanks everybody for coming. Appreciate it. Take care.